Hi. In this video, we're going to go through a few worked examples using Gaussian elimination to solve real-world problems, or approximations or simplifications, at least, of real-world problems. In each case, we're going to start with a plain English representation of the problem, translate that into a mathematical model, solve the problem, and then interpret the result in the context of the problem. As usual, I recommend that with each problem you pause at the presentation of the problem, try to work through the problem on your own, at least as far as you can get, and then come back to take a look to see, continue the video to see my worked solution. So let's start off with this problem, a problem in energy production. A sustainable energy company is developing a strategy for a new region, deploying 3 different types of production facilities: solar arrays, wind farms, and waste combustion plants. Each of these plants has an output that varies with season, and consumer demand that also varies, and consumer demand also varies with season. The exact details of this are all summarized in this table here, with the numbers given in gigawatt hours per day for both production per plant and consumer demand. And the question this company is trying to figure out is how many plants of each type should be deployed given this data. So pause a moment, then come back and continue with the problem. So the first stage in any problem like this is developing or implementing the mathematical model. I always think it's best to start with defining your variables carefully, often just taking the time to think about what are the unknowns, how are we going to define these, really can frame the problem and can help in converting a problem like this into a set of equations. Here, the unknowns are how many plants of each type, right, as given here. Right? So let's define these, a variable for each of these. Let x1 be the number of solar arrays, x2 be the number of wind farms, x3 the number of waste combustion plants, and so on. Right? So these are our variables. If we take a look here, each row here is corresponding to a variable, with the exception of the last one. Right? Now, how can we summarize all of these data and what we're trying to satisfy in equation form? Well, in each season, we have different production levels per plant and a demand. The various plants will produce power, and we would like to produce enough to satisfy the demand. Right? We would like to do this in each season. This gives rise to 4 equations, one for each season, where the left-hand side summarizes the daily energy production, and the right-hand side has the demand. The demand is easy. It's just read off from the bottom row. What is the total energy production? Well, it's the production per plant of each type multiplied by the number of plants of that type, all summed up. And sort of think about this in the context of this table here. And if the number of solar plants is x1, then 4 times x1 gives the total production of energy per day from a solar plant in the spring. The total production from wind in the spring is 6 times x2. The total production from waste in the spring is 4 times x3. We add these up. And our hope is that the sum of these, the total productions, equals the demand. That's exactly what we have written here in this first equation. 4x1 plus 6x2 plus 4x3 equals 70. Essentially just reading down a column. In order to get the equation for summer, fall, and winter, we take exactly the same sort of idea. 10 times x1 plus 11 times x2 plus 4 times x3 equals 125. That's our second equation. Our third equation comes from the last column. 6x plus 10x, 6x1 plus 10x2 plus 4x3 equals 100. And the last equation for winter, 2x1 plus 9x2 plus 4x3 plus 75, as we have here. Right. Supply on the left, demand on the right. We are hoping to solve this system for each of these variables. If we can do that, we have a strategy that would exactly produce the amount of power for the given demand each season. We don't want to produce more, it's wasteful. We don't want to produce less. You don't satisfy demand, you lose customers, you can't sort of provide the service needed by the region. So we now have our system of equations. From this point on, we're ready to shift into more of a pure math mode. Right? System of equations in 3 variables. We wish to solve this system for the value of these variables. Gaussian elimination is the perfect tool to do this. Right? This slide is a little bit busy because it has all of the steps, at least for forward elimination here. But I think it's nice to have it all in one place where we can walk through it. We start with our system of equations form. Right? Exactly the model that we just developed. Our first step is going to be to recast this into augmented matrix form. It's always simpler to work in an augmented matrix where you don't have to carry around all of the variables with you. Do this as a first step. The augmented matrix is very easy to construct. We break it up into one block that corresponds to the left-hand side. 4 variables leads to 4 columns. And we simply take the coefficients of these columns and place them as the 4 columns of the matrix. The right-hand side, the constants, are the last column. Very straightforward. Now we're ready to proceed with Gaussian elimination. Okay? Now, in the very first step, I am going to deviate slightly from standard Gaussian elimination. One thing to keep in mind, when you're working through problems by hand especially, you are always allowed to scale a row. Right? So if you see a row that has larger numbers than you would like to deal with, if there's a common factor that you can divide through by that will simplify things, you're always allowed to do that. If you have a row that's all full of fractions and you want to convert those into whole numbers, you can always multiply by a common denominator and do that. It doesn't change the answer. It doesn't change otherwise the process of Gaussian elimination. You can do this, and it's very common to do this when you're working through things by hand. Right? The first row, every number is even. I find it easier to do arithmetic with smaller numbers. And so the very first thing I'm going to do is this non-standard step of multiplying the first row by a half. That just converts 4, 6, 470 into 2, 3, 2, 35. Makes the next steps a little bit easier because we're not going to need fractions for them. Otherwise, we would have actually needed fractions in the next step, which doesn't change the answers, but makes it easier for us to make simple mistakes. Right? So after this little scaling, let's move forward with Gaussian elimination. We start the top entry. If the leftmost column, and we want to use this as a pivot to eliminate the entries below. We do this by subtracting multiples of the first row from row 2, row 3, and row 4. And the multiples are determined by the coefficient in this entry. To eliminate a 10, we need to subtract 5 times the first row. In order to eliminate a 6, we need to subtract 3 times the first row. And in order to eliminate a 2, we need to subtract just the first row itself. That gives us our first set of operations for Gaussian elimination. Right? Going through that, let's start with the second row. We want to subtract 5 times the first row from the second. 10 minus 10 is 0. 11 minus 15 is negative 4. 4 minus 10 is negative 6. And 125 minus 5 times 35. 5 times 35 is 175. So 125 minus 175 is negative 50. For the third row, 6, we're subtracting 3 times the first row. 6 minus 6 is 0. 10 minus 9 is 1. 4 minus 6 is negative 2. And 100 minus 3 times 35, which is 105, is negative 5. For the last row, we simply subtract the first row. 2 minus 2 is 0. 9 minus 3 is 6. 4 minus 2 is 2. And 75 minus 45, minus 35 is, of course, 40. Right? We've finished our first round of elimination, and we've zeroed out this column. We would move our attention down and to the right to our next pivot. And here, I'm actually going to do a scaling again. I have negative 4 here. I have a row that's all even. Just to make the arithmetic a little bit easier, I'm going to multiply this whole row by a negative half. Negative 4, negative 6, negative 50 becomes 2, 3, 25. With a 0 in the first column. Right? Then carry on as usual. This is our pivot. We want to eliminate below. Right? How do we do this? In order to eliminate a 1, we need to subtract half of this second row. In order to eliminate a 6, we need to subtract 3 times the second row. Our next set of operations based on this pivot. Going through, 1 minus, remember we're subtracting half of the second row for the third. 1 minus 1 is 0. Negative 2 minus 3 halves is negative 7 halves. Negative 5 minus 25 over 2, or 12 and a half, is negative 35 and a half. For the third row, we're subtracting 3 times this row. 6 minus 6 is 0. 2 minus 9 is negative 7. And 40 minus 75 is negative 35. We now have not only successfully zeroed out that first column, we've also done the same for the second, which means we're ready to move down to this entry to use this as a pivot. One more time, we're going to scale in order to simplify, and I'm actually going to do two scalings at the same time. You actually may already notice these two rows are actually multiples of one another, so one of them is going to end up being zeros. You also might notice that they have a common factor, 7 and 35, and 7 and 35 with an extra factor of a half. And so we're just going to scale both of these rows here, multiplying the third row by negative 2 over 7, the fourth row by negative 1 over 7. And that's going to lead us to nice whole numbers of 1 and 5 in both of these positions. Of course, we now use this as a pivot. To do this, we simply subtract the third row from the fourth, leaving us with a row of all zeros as we already might have expected. We now are in our upper triangular form. We have a pivot, and a pivot. All three variables are pivots. This means that already we know that this system has a single unique solution. No free variables, no inconsistencies. We can solve this and get an exact solution. We use back substitution to do so. So, moving on to the back substitution steps. Remember, for back substitution, we start at the bottom row. The bottom row is all zeros, so we move up to the next from bottom. We identify the pivot, the first non-zero entry in that row, and use that to eliminate upwards. To eliminate a 3, we subtract 3 times the third row. To eliminate the 2, we subtract 2 times the third row. In all of the operations, we're subtracting a multiple of the third row from either the first or the second. The arithmetic is easy because we have zeros here already, so there's only really 2 columns we actually have to look at. 3 minus 3 is, of course, 0. 25 minus 15 is 10. 2 minus 2 is 0. 35 minus 10 is 25. We've now successfully zeroed out this whole column. Next step, we've now moved up and over to our next pivot. This pivot is not equal to 1, and so let's divide through, scale this so that it does become 1. Multiply 1/2 by row 2. Replace row 2. That leads us to 1 and 5 instead of 2 and 10. And again, we use this pivot to eliminate upwards. How do we do that? We subtract 3 times the second row from the first. 3 minus 3 is 0. 25 minus 15 is 10. Finally, we move up and over our new pivot. There's no more elimination to do, but we still need to scale this entry. So we multiply that row by 1/2, giving us 1005. Now we are in our reduced row echelon form. We have 3 pivots, each of which is in a row containing only a single entry and everything else zeros. In this form, our answer is really simply sitting there in the last column. This is easily seen by just reading off what these equations mean. The first one is x1 plus 0 equals 5. 0 plus x2 plus 0 equals 5. 0, 0, x3 equals 5. We have our variables, in this case all end up being 5. The last row is equivalent to 0, 0. It's something that we can ignore. We've found our unique mathematical solution. We now cast that back into the language of the original problem. If we deploy 5 plants of each type, 5 solar farms, 5 solar arrays, 5 wind farms, 5 waste combustion plants, given this set of supply and demands, we would perfectly satisfy the demands in all 4 seasons. Okay, let's move on to one more problem, a problem of economic equilibrium. Once again, I recommend that you pause the video after the presentation of the problem, work on it your own, and then restart to see the solution. Here we want to look at a so-called Leontief economic equilibrium model, where we have a national economy broken into 3 sectors. A primary sector, agriculture and natural resources, a secondary sector, manufacturing, and a tertiary sector, services. And we want to take a look at a balanced economy, one where every sector contributes in an equivalent way to the economy and to each other. The production of $1 million worth of output from any one of these sectors requires $0.3 million of input from each of the 3 sectors. So in order to produce $1 million worth of primary sector output, it requires $0.3 million of input from primary sector, $0.3 million from the secondary sector, and $0.3 million from the tertiary sector. On top of this, we have a consumer demand that is $100 million from each sector. Given this structure, what must the total output from each sector be so that the total supply perfectly matches the total demand in every sector? That is, what output, what production levels from each sector would give a balance, an equilibrium in the economy where supply and demand are equal. Okay. Our first step is to cast this word problem into a mathematical model. Again, I always like to start off with variables. What are the things that we don't know about this problem? Well, we don't know the supply from each sector. Let's let xi be the total supply for each of those sectors. There's 3 of them. Call the primary BI equals 1, manufacturing, secondary BI equals 2, tertiary or services BI equals 3. And we'll denote xi to be the supply of each of those. So x1 is the supply of from the agricultural natural resource sector, x2 is the supply from manufacturing, and so on. We don't strictly need this intermediate step, but to be clear about where things come from, I often like to include it. I'm also going to include another unknown, the total demand. We want these 2 things to be equal, but we can conceptualize supply and demand as being 2 separate ideas. Right? The total demand is actually a dependent variable, but we can still denote it as a variable, di. Right? Again, with I corresponding to these same sectors. With these variables, we can describe this in 3 equations. 1 equation for every sector. The total demand in sector 1 comes from 3 places. It comes from 4 places. How much of the product of the primary sector was needed to produce primary sector output. That's here, 0.3 million for every million produced, right? So 0.3x1. To produce manufacturing, secondary sector output also requires 0.3 million of sector 1 output. So there's an additional demand for sector 1 from that. And to produce services, tertiary sector product also needs 0.3 input, 3 million per million of primary sector output. These are the so-called internal demands, the demands that come from other sectors of the economy. And we add to that an external demand or a consumer demand of $100 million. Because of the structure of this, that everything is balanced, every sector requires exactly the same amount of input from each sector, and every sector has exactly the same consumer demand, the other 2 equations are identical. Right? So we have 3 equations that look almost the same, but they have a different demand here. What we would like to find is a consistent solution where the total supply is equal to the total demand. That is, we would like to find a solution where we can replace these di's with xi's and have everything work out perfectly fine. Now, it may look like these are identical. You might be tempted to jump ahead and cross them out because they look like they're duplicated values. They are not. The left-hand side here is different, and so we can't simply kind of get rid of these. And we'll see how these differences come into play in the next section. Now, so our first step is we can make that substitution of the demands equals the supply for all of our I, and this replaces this first column here with xi's. Right? I could write this in a matrix notation, define a variable vector x with x1, x2, x3, a right-hand side vector with 100, 100, 100, and a coefficient matrix of all 0.3s. But if we do that, we end up with a form that looks like this. X equals ax plus b. This isn't in a standard form. This doesn't have all our tools of Gaussian elimination have all been expressed in a form of some matrix times some variable equals some right-hand side. That's not what we have here, but we would like to get there. We can actually, and it's easiest, well, one way to look at it is by looking in this symbolic matrix vector notation as a representation. Can we manipulate this expression in a way that we can transform it into this general form? We can. The first thing we're going to do is we're going to try to move the ax over to the other side to isolate our constants. That gives us x minus ax equals b. But here I have x's in 2 places. I would like to factor out this x. We can't do this without one extra step. As written, what we have here is simply a vector and a matrix times a vector. I can't simply factor out the x, because then I would have what? 1, the scalar 1, minus a. That doesn't make any sense. But I can always multiply any vector or any matrix by an identity matrix. So instead of thinking of this as being 1 times x, I can think of this as being the identity times x. Once we have that, an identity matrix, so this I would be the 3 by 3 identity matrix, because A is 3 by 3, 1, 1, 0 on the diagonal, and zeros, 1, 1, 1 on the diagonal, and zeros everywhere else. Then we can factor out the x, and we have I minus A times x equals B, or exactly the form here, where this piece here is this matrix M. We've converted into a standard form that we know how to work with. What is this matrix M? It is not the standard coefficients, because we need to take I and subtract these from them. Matrix subtraction goes element-wise by element-wise, element by element. So 1 minus 0.3 is 0.7. 0 minus 0.3 is negative 0.3. Because every term in here is either is 0.3, and every term in here is either a 0 or a 1. Every term in the result is either going to be 0.7 along the diagonal, or negative 0.3 everywhere else. Right? This is our coefficient matrix. Not the coefficient matrix that we started with, but the coefficient matrix for this system that is in the standard form. And we can, as always, translate this into a augmented matrix form for solution. Our augmented matrix takes that block of coefficients and simply adds on the right-hand side of B. Now we have this translated into a standard system of equations, a block of coefficients, a right-hand side that we can express in augmented matrix form. We're ready to go through the process of Gaussian elimination. We should start at the upper left corner as a pivot, but once again, the very first thing we see is these are all in decimals. I personally don't like doing arithmetic with decimals, especially trying to do it in my head. And so as a first step, I want to get rid of that. I see that the other rows also have this decimal form. And so as a starting point, I'm just going to scale each row by a factor of 10. Multiply each row by 10. This converts us into all whole numbers. 7, negative 3, negative 3, 1,000, negative 3, 7, negative 3, 1,000, negative 3, negative 3, 7, 1,000. Just to simplify the arithmetic. If you don't want to take this step, you do not have to. Start in this column. Use this as a pivot to eliminate below. In this case, the arithmetic, even with our scaling, is going to get a little bit messier than we've seen in other examples, because we have a leading coefficient of 7 here in the pivot position, which means we need to be subtracting multiples of row 1 that are something of a 7th. In particular, to get rid of this negative 3, we have to add 3/7 of the first row to each of these. So the operation is going to be adding 3/7 of row 1 to either row 2, or to each of row 2 and to row 3. Because the arithmetic is a little bit messier, I'm not going to just expect you to do it in your head. I'll add a little bit of the steps involved. Right? We always construct things so that we end up zeros. Negative 3 plus 3 gives 0. The next step, 7 we are going to be adding negative 3 times 3 over 7, or 7 minus 9 over 7. For the third entry, will be negative 3 minus 9 over 7, as we have here. And for the right-hand side, we'll have 1,000 plus, remember we're adding a multiple of the first row, plus 3/7 of 1,000, or plus 3,000 over 7. Once we've done the arithmetic for the second row, the third row is easy because it's all the same numbers that we're working with. 0 in the first column, negative 3 plus 9 over 7, plus 7 minus 9 over 7. So the same entries that we saw, but flipped in position. And the right-hand side is exactly the same as the one before, 1,000 plus 3,000 over 7. This is just an intermediate step. Let's simplify. 7 is 49/7. 49 minus 9 is 9, so this leads to 40 over 7. Negative 3 is negative 21 over 7. Minus 9 over 7 gives us negative 30 over 7. And 1,000 is 7,000 over 7. So 7,000 over 7 plus 3,000 over 7 is 10,000 over 7. We've already done the simplification for this number, which is negative 30 over 7, and for this number, which is 40 over 7, and for this number, which is negative 10,000 over 7. So actually what looked like a bit of messy arithmetic is, but it's only a couple operations of messy arithmetic. Right? Also, these numbers look a bit nasty to deal with, but we can easily simplify them by another scaling operation. Let's take each of these rows, multiply it by 7 to get rid of the denominator, and divide through by 10 to make the numerators into more kind of handleable numbers. So 7/10 times row 2 and 7/10 times row 3 gives us 4, negative 3, 1,000, negative 3, 4, 1,000. We're back to a matrix form that actually looks quite reasonable, quite manageable. Now that we're in this stage, we continue with Gaussian elimination. Pivot, eliminate. To get rid of a negative 3, we need to multiply the second row by 3/4 and then add. Right? So that's what we do. By construction, negative 3 plus 3 is 0. And we'll have 4 minus 9 over 4. Okay? Because we're multiplying by 3/4. 4 over 4 is 16 over 4. 4 is 16 over 4 minus 9 over 4 is 7/4. This one I did do in without writing the intermediate step. And for the right-hand side, 1,000 plus 3/4 of 1,000. 3/4 of 1,000 is just 750, so 750. This is now our upper echelon form. Pivot, pivot, pivot. All 3 variables are pivots. We have a unique solution. We will have one single solution. We can find it with back substitution. Let's go through that process. We start in the bottom row, identify the pivot. Scale to convert it to 1. We have a 7 over 4, so we multiply this row by 4 over 7. This entry becomes a 1. This number, you might not immediately think that multiplying this by something that's a fraction of 7 would give us a nice clean number, but 1750 is just 7 times 250. So when we divide by 7, we get 250. Multiply by 4, we get 1,000. Nice simple result. Once we've done that scaling, we can use that entry as a pivot to eliminate upwards. We do this by adding 3 times the third row to each of these, as we see here. Our next set of steps. 1 plus 3 is, of course, 0. 1,000 plus 3,000 is 4,000, and 1,000 plus 3,000 is also 4,000. We've eliminated the entries above this pivot. We now move up a row and over to the left to our next pivot. First step, scale. We have a 4, so we want to divide that row through by 4. This gives us 0, 1, 0, 1,000. Then use this pivot of 1 to eliminate upwards. Again, we need to add 3 times the second row. Negative 3 plus 3 is 0. 4,000 plus 3,000 is 7,000. We now have zeroed out the entries in this row, or this column as well as this column. So we move over to our last pivot, and the only thing left to do is scale. And clearly we don't want to divide by 4 here. We want to divide by 7, and we want to do this with row 1. Obviously, I had simply cut and paste from there. That gives us a 1 here, and 7,000 over 7 is, of course, 1,000. This is our reduced row echelon 4. Pivots all equal to 1, all by themselves in a column. We can directly read off the answer. x1 equals 1,000, x2 equals 1,000, x3 equals 1,000. It's not surprising that the system that was set up to be perfectly balanced, we told you everything was sort of equal, each sector was treated exactly equally. It would be very surprising if we did not end up with the same numbers out of this. This is our mathematical solution. Last step is to phrase this back in the language of the original problem. Those thousands are thousands of millions of dollars. So each sector must produce 1,000 million or $1 billion of output in order to satisfy the consumer demand and the internal demands needed by the other sectors in order to produce this, right? This actually leads to, wasn't part of the question, but leads to an interesting observation that the consumer demand, the external demand, represents only 10% of the total demand. There's only a demand of 100 million from each sector, but in order to produce this, each sector actually needs to produce 1 billion. Okay, so those were 2 examples highlighting how we can use Gaussian elimination to solve real-world problems, giving a little bit of extra practice in the process of Gaussian elimination, especially with systems where the numbers are a little bit less contrived, and thus where the arithmetic becomes a little bit more, a little less trivial perhaps, and also gives us a bit of extra practice in framing mathematical models and interpreting solutions in the context of those. This is our last video for Unit 3. Thank you and goodbye.